All right, welcome to part 2 of chapter 9. We're going to talk about reactions of alkynes. We left off talking about acidity, but let's focus on the triple bond. This is where we're going to see some comparisons to the alkene reactions. First, we're going to look at reduction. Now, there are 3 different reductions that we are going to see in this chapter. The first one should look very familiar, right? It is just catalytic hydrogenation. Now, again, that can be platinum, it could be palladium, it could be nickel, right? You're looking for a metal catalyst there. That is going to do the same thing it does with alkenes. It's going to take it all the way down to the alkane. Instead of adding H2 across a double bond, you're adding 2 equivalents of H2 across a triple bond. All right. Now, it does go through this intermediate, and it is a syn addition, but you cannot stop it. So you don't really need to know that it has an intermediate. It's going to go all the way to the alkane. What if we want to stop it, though, at an alkene? Right? Remember, we are control freaks here. This would be what I would consider a full reduction. Right? It's completely reducing. It's increasing bonds to hydrogen. We're going to have 2 different partial reductions. Right? So 2 and 3 are going to fall into this category where we are going to wind up with an alkene. Right? It's not going to go all the way down to the alkane. And we're going to be able to control the stereochemistry. So if we take our triple bond and we treat it with a poisoned catalyst, we can get a cis alkene. There are different catalysts that work here, but you are going to be responsible for Lindlar's. And you really just need to know the name, right? It's Lindlar's catalyst and H2. You still need the hydrogen. And you'll notice here the hydrogen's on top, the catalyst is on the bottom. I don't care how you put that on there. They're both necessary for this partial reduction. You do not need to memorize the formula for Lindlar's catalyst, but what you do need to memorize is the name. You need to memorize the name, and you need to memorize the stereochemistry. You do not need to know the mechanism of this reaction. It is more complicated. You'll see Klein doesn't even tell you, right? It's the first step that's catalyzed, and then the second isn't, so you can stop it here. This is really all you need to know in terms of Lindlar's catalyst. This is a way to take a triple bond to a cis alkene. One that we're going to take a little bit more time with is making the trans alkene. Right, so it's another partial reduction. You're going to take your triple bond and you're going to treat it with sodium, just sodium metal in ammonia. Now, we've worked with sodium amide, NaNH2, quite a bit. This is different. You need to recognize the difference. NaNH2, right, I'll just write it over here because it won't last. This is a salt. NaNH2 is an amide ion that's going to be a strong base. This is sodium metal. This is really important, and you'll see in the first step of the mechanism. But this is going to allow us to stop at the trans alkene. This is called a dissolving metal reduction because you have dissolved your sodium metal in ammonia, and then it reduces. Now, the first 2, you don't need to know the mechanism, but we are going to look at the mechanism of our dissolving metal reduction. It, of course, is over here on Klein in your slides. You know me, I need to draw while I talk. All right, so we have our triple bond. This is why it's so important that you have sodium and not a sodium ion. You need that electron, that additional electron that's easy to remove. This is a good mechanism, and I really enjoy this one because it forces you to think about the type of arrow you're using. The first step is just the movement of a single electron. So So you use a single barbed arrow. We cannot have more than 8 electrons on carbon, so one of our pi bonds splits. We wind up with a radical a radical anion. On one side, we wound up with a lone pair. It's going to be a negative charge. And on the other side, we round up with a radical. There's no rotation around this double bond. It's what helps this stay as a trans product. From here, the ammonia is going to provide us with the protons. Right? Ammonia is not particularly acidic, but a negatively charged carbon, especially a negatively charged sp2 carbon, is going to be more reactive, and it is going to steal that hydrogen. You are going to now wind up with a radical. Right? So we went from radical anion to radical. And now we're going to go to an anion. Another atom of sodium is going to donate that electron. And you're going to wind up with your anion. Right? So it goes radical anion, radical anion. And then in the last step, you're just going to protonate again from your ammonia. And so you will wind up making some NaNH2, but that is not the reagent. You are responsible for this mechanism. Make sure to practice it. Make sure you pay attention, right? Double barb versus single barb arrows, right? You not only need to care about where the arrow originates from, where it winds up, but also what does the head of the arrow communicate. You definitely practice that one, please. This, of course, Klein steps you through this mechanism in a slower way. It explains why you can't get rotation, why the trans is going to be the major product, but I'm going to skip through that. We talked through the mechanism. That is good information for you. Now, we're going to start getting lots of cool summary slides from Klein. These are great for studying, and they are really helpful when you do multi-step synthesis. You can just graphically see all these different options that you've learned. You can go from a triple bond to a double bond, cis or trans. You can go from a triple bond, any kind of double bond, to an alkane using H2 and a catalyst. We're going to move on to hydrohalogenation next. We've added HX to alkenes before, and we know that that's a Markovnikov reaction. You can add it also to a triple bond, and it will also be a Markovnikov reaction. It really depends on how much you use, whether you're going to stop at this halogenated alkene or if you're going to make the gem dihalide, right? But if you are taking that triple bond, right, and you see either, let's say, XS, that's how I abbreviate XS, XS HBr, right? Or perhaps you're going to see 2 equivalents of HBr. Essentially, if you have enough, it will add twice. And the first one is going to put the bromine on the more substituted side. And then the second addition will put the bromine on the more substituted side. So you get a geminal dihalide. You are responsible for predicting those products. You won't be responsible for the mechanism. The initial part of the mechanism is very similar to what we've done before, but vinyl carbocations are so unstable. Even Klein says this mechanism is unlikely. If the book says that the mechanism is unlikely, I'm not going to ask you to memorize it. So what I want you to remember is the reagent, be able to predict the products, know the stereochemistry, Markovnikov. And know that it makes a geminal dihalide when you have enough HX. Just more discussion on the mechanism. Again, you will not need to know the mechanism. It is interesting, and if you want just some light mechanism reading, you have a few slides in here that are helpful. Something that we will not be surprised to see is that if we add in peroxides, we can get anti-Markovnikov. HBr and our peroxides. This only works, notice, with HBr. I'm not going to trick you. I'll only give you HBr. You'll notice we use bromine most of the time. It just works the best in a lot of these reactions. The Markovnikov just with alkenes. Okay. If you just have one equivalent, you just have enough to add it once, it will go to the less substituted side, right? So it is anti-Markovnikov. This would be another radical mechanism that we will cover this type of radical mechanism in chapter 10. Right now, the only radical, quote-unquote, mechanism that you know is the one we just did with the dissolving metal reduction, and that is half radical, half not. Okay, so there are a few different things to take away from this. We now know how to make an alkyne from a dihalide, and we can make a dihalide from an alkyne. We're getting a lot more control by having more options synthetically, which will allow us to solve bigger, more interesting problems later. All right, this reaction